Uniformly accelerated motion is one of the most basic things that you need to know from physics. And I don't mean basic as in easy, I mean basic as in base, as in a lot of things really hinge upon this, especially an understanding of it. So I'd like to maybe go a little bit by contrast and talk about what happens when you're not accelerating. So see, if you're actually not accelerating, then it becomes really, really easy. Okay, if you're not accelerating, you have nice, easy equations of motion. In this case right here, your speed or your velocity will just be equal to your distance or displacement divided by t here. So it'll be s over t. Some people call it distance over time. That's also fine. Right, so something like this in seconds, and this is in meters. So in this case right here, super, super easy. Okay, if not accelerating, really, really easy. I love this picture here, accelerate to attack speed. So there are 4 equations of motion. You really need to know these ones right here. You don't have to know them by heart because they're on your data booklet, but you do need to know how to use them. There's one extra one that's really important, I think, as well, so I'm going to actually put it down here. It's sort of a general definition of acceleration. If you're accelerating, it's your change in velocity versus time. Technically, it's a vector, so I'm going to be really careful here and actually go like this. So this right here is your acceleration is technically the change in velocity over a change in time. That is sort of a key thing in physics. So maybe we'll talk about this. If you're accelerating, remember it means your speed is actually changing with time. What that means, imagine if you're driving in your car. If you're going at a constant velocity, if your velocity is constant, then you're not accelerating. Right? That's maybe we should say v equals constant. So if your velocity is constant, you're not accelerating. So what that means, then you could still be in motion, right? Because you're not accelerating doesn't mean you have to be stopped. You could still be moving, right? You could be in your car going at 100 kilometers an hour. So if you're driving at a constant 100 kilometers an hour, think about your speedometer. Or if you have digital one, then, you know. But the numbers will actually just remain the same. You'll be just at 100. You're not changing. Therefore, you're not accelerating. If you are accelerating, that means your velocity is changing. Do you see it came from that literal definition here? That acceleration is a change in velocity. So anytime your speed or velocity is changing, you've got some sort of acceleration here. Now there are these 4 main equations of motion which you don't have to memorize, but they go v equals u plus at. You've got s equals ut plus half at squared. You've got v squared is u squared plus 2as. You got the other one here with s equals v plus u times t over 2. It's important to make sure you know what all these different letters mean. So that's why I'm going to add to them here. So remember that s is your displacement. I always thought that was strange that they call it displacement, right? Why do they call s displacement? You'd think it should be called d, right? But s is displacement, and that's in meters. Actually, there's a reason. I mean, there's a lot of reasons why, but it just seems silly, I think, to an IB student at least. Like, what is it? Displacement? But I mean, if you think about if you're doing calculus with all this stuff, like with derivatives, we use the symbols d, dx, and things like that. Then it gets really confusing. So that's why, okay, displacement is fine with an s. Initial velocity. Or initial speed. We'll use these as a vector ones actually, so this will be good. So technically, I suppose they should all have little vector symbols on top of them here. So should this and this and this. These are all vectors. You know the difference between vectors and scalars. See, time is a scalar, so you don't have to worry about it. But this is technically how it should go here. So if we do this, the initial velocity is going to be measured in, you know what velocity is. It's a rate of change of position. So in this case, remember velocity is change in displacement over time. That's how you can define velocity. And if you define it that way, then you can say, look at the units of this thing. Look, it's like a slope, isn't it? In fact, if you have a graph of displacement versus time, right? Displacement is in meters, time is in seconds. You have a graph of displacement versus time, I don't know, maybe it does something like this. The velocity is just going to be, let's see, delta s, delta t. That's the slope of the tangent. So what that tells you then, for example, right up here, can you see the tangent line right here be flat? That tells you then that the speed right here, or the velocity right here, is going to be 0 because the slope is 0 right here. Over here, speed is positive. Over here, speed is negative. So let's go into this units then. If the velocity is dependent on the displacement, the units of displacement are meters, units of time are seconds, so that's why it says meters per second. I'm just trying to show you where everything came from. Like I said, it's a basic because it's a base. Final velocity, same thing. Because remember, if you're going to accelerate, you're changing your velocity. So what does it start off at and what does it finish at? That's u and v. Acceleration is literally this thing right here you're talking about here. It's this change in v versus t. And again, look at the units. Doesn't V have units of meters per second? Right, we just talked about it right here. Right? V has units of meters per second, and you're dividing by seconds. So it's meters per second. That's why it's meters per second squared. That's why I write it like that, meters per second squared. Time, of course, is in seconds. We're going to say S, but I like to put seconds. So these are these main equations that you need. These are the different letters, different variables you're going to be using. Now, there's a nice little trick here for solving lots of acceleration equations. I like to call it UVAT. Some people call it SUVAT. It doesn't matter. But basically, you should use this sort of trick here. At least I think it's a good way to do it. If you're not super good at this, it's a good trick. What I like to do is, this basically tells you your shopping list. So what I would do is I would, split up. I would actually write down, what do I know? Do I know what U is? Do I know V? Do I know A, S, and T? If I don't know something, I put a question mark. If it's the thing I want, I put a star. I'm really careful with pluses and minuses if it goes up or down or whatever. And I always make sure that the only things that go in here are in proper units. In other words, if they're being sneaky and they gave you something in centimeters, let's just say, make sure you convert that to meters. So in my own rules, at least that's how I deal with this. And maybe let's actually do an example. So here you're driving in your car. Oh, by the way, I like this. Decelerate, because you're going to be talking about decelerating. I like to decelerate to regurgitate the celery you just ate. So you're driving in your car and you're going 21 meters per second. Just the notation is a bit weird, but basically your initial speed, remember, initially you're going this. So that means U now is 21 meters per second. You slam on the brakes. What that means is you slow down, don't you? You decelerate at 3.2 meters per second squared. So acceleration is 3.2 meters per second squared. But you got to watch out here. If you're decelerating, let's just assume you're going to the right. Let's just maybe assume that. So we'll draw our little situation here. So here's your car. I'm a really lousy artist, as you can see. So your car is initially going with some speed 21 meters per second. And what happens, of course, at some point, you're going to be stopped, won't you? So at some point, oh God, my drawing got even worse. My speed is 0. So to do this, think about this. What's the direction of my acceleration? My acceleration has to have an opposite sign to the speed. Because you see, if the speed is going to the right, then you need to define your acceleration as to the left. So I'm going to put a negative in front of it. Just because the acceleration, otherwise the acceleration would be positive 3.2. That means you'd be starting at 21 meters per second. And you'd accelerate, like, you'd actually, put on the gas. And you'd end up going way faster. And that's not the situation here. So somehow you have to account for it. I like to just make my initial speeds in the positive direction, and anything that acts opposite to that, I just throw a negative in front. So how long does it take for you to stop? How long? That implies a time. So this is what we're looking for here. So what I'd like to do then is just show you that whole UVAS thing, or SUVAT, or whatever you like to do here. I just put in what I know and what I don't know. This helps me to pick which equation I should use. So U, the initial speed, is easy. It's 21. It's meters per second, so it works. V, the final speed, think about it, you stopped. So there, V is 0. So that's why this is 0 here. Acceleration in this case is negative 3.2 because, again, you're acting in the opposite direction. If you didn't do this, you couldn't have V here be 0. Your displacement, I don't really know it, and I don't really care. I'm going to put a question mark, like don't know, don't care. And T, oh, that's what I want. I put a star by that. So what this does, this is like my shopping list. This tells me what to do. Look carefully here. I've got my time. And what I want to do is I want to solve for time. In order to do that, then what I should do is find an equation that doesn't have S in it, but that has time in it. So I need an equation with no S's, but that has T. Let's see if we can find one here from these. Do I have an equation that has no S's? Well, that means it only has to be the first one here. V equals U plus AT. If you're going to solve it, you should always write down which equation you're using. So I'll say V equals U plus AT. That shows your examiner you know what you're doing. Then you actually just put in the numbers. So let's just see if we can figure it out here. So I would say then that, well, I can solve for T. I can get T by itself. Remember, V is 0. That's really easy. So let's see, I have negative U equals AT, because I moved my U over. And then to get T, then I have negative U over A. So in this case here, the time is going to be negative U, which is 21 meters per second, over A, which is, remember I called it negative 3.2. So see, it works out. The time isn't negative. If you're really careful with this stuff, units will always work out. In this case here, you get 21 over 3.2, which is, what's that? I'm using my trusty calculator here. I get an answer of T equals 6.5625. What kind of digits should I be using? Do you notice I have two numbers here to represent this and two numbers to represent this? So I have to do the same. So I will state then that my time is going to be 6 point, in this case I'll round 1 after. So it'll be 6.6 seconds. See? We can solve.